about the problems that we face in Earth and space science and atmospheric science to cluster orientation data. And Klose, my colleague in Berlin, Germany, we developed an algorithm that is published, and we'll talk about this algorithm a little bit. First of all, introduction. As I said, we have problems of clustering directional, bidirectional data, and in the past, we go back 100 years, counting methods were developed where people tried to count how many orientation vectors we have in certain directions. I showed some figures in a bit. And later on, and these were automized then in the 70s, and in continuation, they were improved. Stochastic assignment of orientation vectors, such algorithms were developed in the 80s and 90s, and then fuzzy set theory was implemented, certain distance measure to measure the distance between different orientation vectors. And here we see what we mean about orientation vector. Measure a certain angle or two different angles in the orientation of a vector. Let's say we have a star in a certain direction, or we want to measure the orientation of a plane in a 3D space. And the plane is bidirectional data. We have a normal vector on this plane, basically two normal vectors. So in this case, because the approach was developed, or our approach was developed for clustering plane data, and the normal vector of this plane, basically we can present in a unit sphere, project this on the lower hemisphere of this unit sphere, and then we can project this back on this equator here, and this data points, these data points present the orientation vectors basically. And these are the counting methods. We see here a higher density and here a higher density. So still practitioners use these plots to say, okay, it's more or less in this direction, it's more or less in this direction. But we have sampling biases. For example, if we have planes in 3D space and we cannot go access, we don't have access into these 3D spaces. We only have access on the front of a wall. Let's say we build a tunnel and we cannot look inside the rock. We have to look at the surface, and we can only measure then how many, what the orientation of these flexures are, or these planes are, and how many we count. But if a plane is almost parallel to the plane we measure, the window we measure, we do not detect many of these data points, and therefore we cannot have a good, a nice density distribution here. So we need, this is what we thought, we need another approach. And the improvements that were made to cluster, to develop an optimized system to cluster these orientation data, they were a little cumbersome because they tried to develop probability distribution of these mean vectors for these data distributions. And in order to optimize, to calculate the mean orientation of all these different clusters, the assignment of a data point to a cluster, and then the adjustment of the mean vector. These two steps, basically, you use an EEM algorithm, these two steps were based on different cost functions, and this is kind of not optimal. And we like to improve that, and where we have the assignment and the adjustment based on the same cost function. Here again, a little bit to the definition. We define a pole vector based on two angles, and these angles are these intervals. We can also present each pole vector in a Cartesian coordinates, and we can, very simplistic. Here again, we have here the data point on the unit sphere in the Cartesian coordinates, and we have here the two angles. So our algorithm is based on vector quantization. We basically say we assign a pole vector, and this is now extremely simplistic. We say a certain pole vector or a certain data point belongs to a cluster with a 1 and does not belong to with a 0. So it's a hard clustering algorithm basically. And then we want to minimize these cost function, the distance as a function with respect to the assignment over all data points over all clusters, and this has to be minimized, as I said. So the minimization is performed iteratively in two steps. As I said, we have the expectation step, where we assign whether the data point belongs to a cluster or not. And then we have the minimization step, where we have where we minimize basically our overall costs. So here, very simple. We have a loop. You select a data point. We assign a data point to a cluster. We look which cluster is closest to this data point, and then we adjust the mean orientation of each of this selected cluster. And we have a learning rate here, because we talk about machine learning algorithm, where the algorithm tries to learn and optimize, and this learning rate has to be defined as well. I will do this in a bit. I'll talk about this. One thing I would like to mention also, distance between orientation vectors. As I said, we have bidirectional data. So if we have a plane that is almost perpendicular to the ground, this plane can be oriented in this way or in this way. So in our unit sphere, these data points would be on different sides. So what we need is a distance measure that says we have parallel vectors, they are similar, orthogonal vectors are dissimilar, and anti-parallel vectors are similar again. So for the distance measure, we basically use the arc length on the unit sphere. So we use an online algorithm because we present now each data point to the algorithm, and that's called online clustering. So it starts, we initialize our pole vectors. Our annealing schedule is determined. The learning rate basically has to fulfill a condition that it has to decrease over time, because more and more we actually have experiences and we don't need to learn that much anymore. And the mean vectors of our clusters we determine are moving into an optimum. And then we have to define how many iterations we want to have a maximum. We start with a 0 iteration. We basically compute from our two angles the Cartesian coordinates for each pole vector. We can do this randomly, or we just choose a certain data point. And then we repeat. Basically, we draw from our sample data one data point. We present this to our mean vectors. We calculate the distance, and then we say, okay, which cluster mean vector belongs to the selected data point. And then we basically have to compute these parameters for this new step. We adjust basically the orientation of the mean vector, and then we compute the Cartesian coordinates for this pole vector, and then the learning rate has to be adjusted again because it has to decrease over time, and we do this until the end of our maximum iteration. And then we have to do our problem we had with the bidirectional data. We have to project this to the lower hemisphere, and we have to adjust for anti-parallel vectors that the parallel and anti-parallel vectors are similar. So here's an application. I showed you initially these data points, these little black dots, and now we can have density distribution on these data points. And this is we call now the ground truth. It's a data, a group of data that were chosen that they have 3 cluster mean orientations, and this is called the ground truth. And these guys, they published this, and basically you could almost say, wow, it's almost random, but it's not. And they calculated, came up with these numbers, and we basically applied our algorithm, compared this to this result, and to another algorithm that is out there. This is the other algorithm that's out there. They basically have for the cluster 1, basically 26% off, misclassified 21% here and 11% here. And you see here these little larger circles would be one cluster. If I go back, let's start here again. It would be one cluster here. Then we have a cluster here that comes also on this side. And then we have here a cluster which goes on this side. And this is, again, we have almost a 25 or 25% average misclassified. And the algorithm we applied now, we have a 7% difference in orientation, 3% for the other cluster here, and 0% for the third cluster. So we see already that there is less misclassification if we have really a nice distribution in the center. But if we have, due to the sampling errors, sometimes we have not enough data points, certainly we have a higher uncertainty in order to determine the optimal orientation. Yeah, and this algorithm, oops, I'm almost finished, but not that quick. Sorry. And even this algorithm is again simplistic because it's a hard clustering algorithm. And next steps to improve is we like to look at subclustering algorithm where we have basically a probabilistic approach. We just assign a certain data point to a cluster based on its probability. But here I like to say that this algorithm is now it's online. I just put it on this page now here, and we have here certain data points. You can easily use this app, and you have to define whether you have pole vectors or plane vectors. Here it's another improvement that we're working on. If you have orientation and additional feature, like you have an intensity, or you have for earth science, you have the length of a plane, the size of a plane. You have small planes and large planes. You can add features here, but it's not implemented yet. It's just a placeholder here for now. And then you can calculate, you have to define how many clusters you think you see or you have. I think still it's a very subjective decision. I personally believe there's nothing objective to say it's now. I mean, here we would say, okay, it's 4, but the data sample we saw before, it was very almost random. And then you choose the number of data points, you choose the maximum iteration steps, and then you can visualize basically here. You see here the difference is now the clustering, this cluster on this side, and then you can scroll here through and see different cluster they light up, and you can also, as an output, you can save all these data in new files. So you have the original assignment of a data point and the new assignment that's belonging to a certain cluster. In conclusion, we partition data points into isotropic clusters. Another improvement when we want to make a subclustering, sometimes we don't have an isotropic, we have a griddle distribution that have a long elongated distribution on the unit sphere. We analyze the average orientation of these mean vectors, and this is a self-consistent method basically because the m steps based on the same cost function that we optimize or minimize. We do not require any special pre-processing on that, and this is what I mentioned already. The soft clustering is the next step, and to include also additional features. And here's an example, showed magnetic data distribution of the Earth on the north and southern hemisphere, and the question would be now, what is the orientation, and do we see fluctuations over time? Because you can apply this also in time steps if clusters basically fluctuate over time. And I think that was the last part. Thank you. The question was, having a soft clustering algorithm, would it be easier or harder to cluster? Easier in terms of speed, it's harder. Easier in terms of finding a nice cost function, I think it's not hard. And the other question shapes of distributions, like you have elongated distributions, like if you plot the Mercury on a unit scale, you would have a griddle distribution. And that might be a little heuristic. You have to apply what you want to focus on. I mean, that's probably the face this problem when we handle. That was, yeah.
One thing I didn't understand, if you take the normals to two planes, which are very close to each other, you have one normal pointing this way, and the other normal pointing in the opposite hemisphere, but those two planes are really very, very similar.
Yes.
Whereas, if you look at, for example, your last slide here, you're looking at magnetic and weather data on opposite sides of the Earth.
Yeah.
There is no 180 degree degeneracy.
That's simplistic. That was a specific problem. And you can change the distance measure basically and apply it where the issue is. I mean, I explained it to having plane orientation in cluster these data. But, yeah.
My question was, I mean, you covered this in the comparisons. I mean, you can always embed your surface in a higher dimensional space where you can do the usual plus that humans are used to. How would this compare against those techniques, massive high dimensional, small ordination?
I mean, good question. I mean, it depends on what, I mean, if you have a higher dimension orientation data as well, you just simply add more features and the algorithm becomes, it's not that fast anymore. I mean, it's just a question of speed then. But the principle of the problem is the same. This is my answer. Yeah. There's only a question of dimensionality and then of speed. That's it. But if somebody has another answer to this question, I would answer this that way.
Suppose the previously considered in higher dimensions, the cluster coordinates that won't necessarily be part of your original space. So maybe that's interesting. And this is better because you always get a cluster which is part of the natural space for the data.
Do you have a few minutes? Can you talk a little bit about the other two methods you mentioned? You just mentioned that they compared.
They're not, this is the project that we are doing and planning to do.
But
Of the soft clustering, you mean? Or you mean the other methods
The original methods.
You mentioned
Okay.
two other original methods, but you didn't say anything about them. You just quoted the
Okay.
authors, and I don't
Yeah.
know what those methods are. Could you say what those methods are? Like, yeah,
So
this method.
let's start with this. The very original methods, they basically say we try to, we want to determine our kernels, or probability, or density distribution. It's basically a histogram. And I just count basically and see then the density, and where the highest density is, you have the mean orientation. That's it. And so, but you don't have really an assignment of cluster, of the data points to the cluster. The other algorithm, the improvements were where you define a mean orientation, you calculate a probability distribution for this mean orientation, and this could be already a griddle distribution. And there are many, there are Bingham and Kent distribution, there are many kinds of distributions in order to define these data points. And then if you assign, you based on this distribution, you have your mean vector of your cluster. And then if you present a new data point, you calculate the distance, which was done here before. They used these fuzzy sets here. This is the distance they use. If you use the arc length, you basically have the same. And based on this distance, you make a reassignment of your mean vector. But you determine the probability distribution for this mean vector, which is a complete different approach and has nothing to do with having one solid cost function that is applied for the expectation and maximization step. So these algorithms work, but I think they're not following the way a custom algorithm should work. It's heuristics. I think there's more heuristics involved. That's the bottom line. So. Well, I have one question. I don't know, is there 5 or still time?
If you're willing to have spheres that are bigger than 3 dimensions, there are applications for these kinds of methods in psychology or psychometrics. You will measure tests and you will correlate. Correlations can be represented by a cosine. It's an ongoing issue when we have lots of tests. Are there just some chunky ideas for this group of tests versus that group?
In terms of size.